I'm dressed up today as a professional. For those who know me, you know that's not a joke. This is not my usual attire, but you notice I didn't say I'm dressed up as a professor, because if I wanted to dress up as a professor, I would have my tweed jacket on, my flood pants, my sandals, and my white socks. But because of the inclement weather today, I decided that I wouldn't dress up as a professor, I'd dress up as a professional. So, welcome, ladies and gentlemen. Dr. Daphne Schiff, Dean Hasty will be late, I think, today. Honored guests, ladies and gentlemen, you all know me. I'm Rob McLaren, Director of the Center for Atmospheric Chemistry, so as usual, it's my pleasure to be able to be the MC for the proceedings for this afternoon for the 23rd Harold Schiff Lecture in Atmospheric Chemistry. Welcome, Don. And we will talk about numbers today. It is the 23rd, so I wanted you to pay attention to that. It's the 23rd Harold Schiff Lecture Series. The first was held in 1990. I actually went to the archives. In 1990, we had a kickoff lecture to celebrate the lecture series, so we had a whole bunch of speakers come. We had people, those who are atmospheric chemists will recognize the names. Paul Crutzen, who had not won the Nobel Prize at that time, but did win it in 1995. Brian Ridley, Fred Fazenfeld, who is still around at NOAA, Jack Calvert, Ralph Cicerone. So these are some names that if you go back, students, if you go back into the literature, these are very famous names that you'll run into, of course. And those are all people who have been here to speak in this lecture series. Our speaker today is Professor Astrid Kiendler-Scharr. Welcome from the University of Cologne in Germany. And I have a few proceedings before I introduce you. So we have some other business to take care of, some awards and things like that. So I will introduce our speaker in a few minutes' time. First, I wanted just to say a few words about the Harold Schiff Lecture Series, as I always do. The lecture was established in honor of Harold Schiff, you can all see, who was York's founding Dean of the Faculty of Science in 1965. Among his numerous achievements were his major contributions to the development of techniques for measuring trace constituents in the upper atmosphere and the lower atmosphere, and to the interpretation of the chemistry and physics of the stratosphere. I first met him after he retired at a conference down in the States when he was selling instruments. I hadn't met him here at York. He was an educator and scientist in the field of chemistry. Schiff began at York in 1964 and was named a member of York's Founders Society in honor of his contributions to the early development of the university. While at York, Schiff was the chair of the Department of Chemistry. He was the director of the Natural Science Program. He was the dean of the Faculty of Science, as I said, the founding dean from 65 till 72, and he was also the founding director of the Center for Atmospheric Chemistry, which started in 1985, and we're going on 28 years right now for that center. Currently, the Schiff Lecture is organized by the Center for Atmospheric Chemistry, and it's sponsored by the Department of Chemistry here at York. We actually had a discussion with Tom McLagan about trying to find a way to find some funding for this lecture series. Right now, it's just the Department of Chemistry, through the Faculty of Science, pays for the lecture series. So we approached Tom to see what he could do. And we're going to invite Tom up to say a few words. He's just going to take a couple of minutes.
Yeah, very few seconds indeed. I'm Tom McLagan, and I'm the Senior Development Officer for the Faculty of Science, which means I deal with sort of donor issues and so on. And we're just taking note, as I discussed with the Center for Atmospheric Chemistry, the fact that not only is our 50th anniversary of our faculty coming up in 2015, which is also, of course, the 50th anniversary of Dr. Schiff's time with us as our inaugural dean. It's also in that same year going to be the 25th anniversary of this lecture series, and it will be the 30th anniversary of the inauguration of the Center for Atmospheric Chemistry, of which Dr. Schiff was the inaugural director. So it seemed very fitting that we would take the opportunity, if we can, over the next 18 months perhaps or so on, to see if people would like to financially support the lecture. where all of us who are around the university these days understand the financial pressures that different units within the university are under, and we just want to make sure that the longevity of the lecture continues for a good long time. And so all that I wanted to do is really just say that if you're interested in that sort of thing and would like to support the lecture to, again, ensure its longevity for long, long into the future, then please, you can speak with myself or with Rob or with Dean Hasty, and I'll just leave it at that. So thanks, and I think that's all for me.
Thanks, Tom. Okay, now we get to the fun part. We like to give out we have a graduate awards in atmospheric chemistry named after Harold Schiff, and so we like to hand those out at this series. So I missed giving them out in 2012, so we're going to hand out two today. We're going to hand out the awards for 2012 and also for 2013, the Harold Schiff Graduate Student Awards in Atmospheric Chemistry. So, Amanda Jameer, could you come up? So Amanda is working with Professor Hasty. The Graduate Student Award is given to an incoming graduate student who has shown excellence in research. Congratulations. Are you okay? And our 2013 award winner was Zoe Davis. Zoe, come on up.
Thank you.
Zoe's working for me. Complete. Thank you very much. Okay, now I get to introduce our speaker for today, who's been waiting patiently here, Professor Astrid Kiendler-Scharr. Just a short biography of her. She studied, I want you to pay attention to the universities. These would be really nice places if I had this type of biography. She studied physics at the University of Innsbruck in Austria. In '96, she got a diploma in physics at the University of Innsbruck as well. In the Institute for Ion Physics. She then went to the Max Planck Institute and worked in nuclear physics, the atmospheric physics division in Heidelberg, and received her PhD in 1999. I've done some translations from German to English, so if I get them wrong, you'll have to excuse me. She did her habilitation, so that's one level above the PhD before you become a professor in Europe, at the University of Cologne in Germany. I'm not sure if I pronounced that correctly either. University of Cologne. In the meteorology department, formation of secondary organic aerosols from biogenic emissions of volatile organic compounds, which is very close to the title of her talk today as well. She, in 2011, became head of the group Stable Isotopes and Aerosols at the Institute for Energy and Climate Research in Jülich, known as IEK-8. In 2012, she became the director at IEK-8 in the Tropospheric Research Section in Jülich, and since December 2012, became a professor of experimental physics at the University of Cologne. I was looking up some of these universities, and I realized that the University of Cologne is one of the oldest universities in Europe. Very large, 38,000 students and 4,000 postgraduates. One of the largest universities in Germany. If not the oldest, it's one of the oldest. It was founded in, anybody want to guess who doesn't know? 1860. Let's have another guess.
That's sweet. That's a new one.
1400. That's pretty close. Pretty close. 1388. It is 625 years old, if my math is not incorrect. So just to put that in perspective, in 1388, that was just a few decades after the Black Death or the Black Plague in Europe. It was perhaps not coincidentally the end of the Dark Ages and the beginning of the Renaissance about that time. So that's an interesting bit of history from that university. Professor Kiendler-Scharr has a few awards. She has some undergraduate awards. From 2006, she won the Young Investigator Group Award, Stable Isotopes and Aerosols. 2009, a member of the Helmholtz Academy for Executive Managers in Sciences, and in 2012, a Helmholtz Excellence Professorship. The title of her presentation today really tells us what her research interests are. She's going to speak about chemistry-climate interactions, biogenic emissions, and their contribution to secondary organic aerosol. Ladies and gentlemen, please welcome Professor Astrid Kiendler-Scharr.
Thanks for the nice introduction, and thanks everybody for coming here. Thanks for having me here for the Schiff lecture. As you heard already, I'm going to talk about chemistry-climate interactions and how biogenic emissions and their contribution to secondary organic aerosol do have to do with the climate in general. Before I start explaining that, I wanted to make sure that those of you not dealing with atmospheric chemistry in everyday life understand what aerosols are. So strictly speaking, an aerosol is a liquid or solid particle suspended by the air. So it really refers to the whole system particle and gas phase, whereas many times when one speaks of the particle phase, that's really what one means with the aerosol. In the atmosphere, particles do cover large size ranges going from a few nanometers to tens of micrometers in diameter, and they do have very variable inorganic and organic composition, which can be either externally mixed, meaning individual particles having different components in them, or internally mixed, meaning one particle having both inorganic and organic composition in it. What you see here is a picture from one of the big cities in China. Particles do affect visibility. They do affect air quality, which is partly a motivation to study particles. But on the other hand, particles are also impacting on the climate. So what you do see here is a summary of the radiative forcing of different kinds of components in the atmosphere from the recent IPCC report. And what is summarized here, everything going to the positive values here is species which are having a warming effect on the climate. So that's really the greenhouse gases up here. And then here in this red box, you see the effects of particles. And an interesting aspect of the particles in the climate system is that they are considered to be cooling. So what you see here is different components, different parts of the composition of the particles adding up to direct effect of a cooling, where the particles themselves scatter radiation and by that insert a cooling effect. And then on the other hand, this lower part here, where the particles, because they act as cloud condensation nuclei, also have a cooling effect, which is called an indirect effect, because the real cooling part comes from the cloud that is formed with the particles. Okay, what you see here also is that there are huge error bars here, which indicates that the scientific level of understanding is much lower for the aerosols than, for instance, for the carbon dioxide warming effect from greenhouse gases. So that is certainly one of the motivations why having a closer look into particles is an interesting thing to do. So I already mentioned that parts of the different composition aspects do have the cooling effect. So if we have a look into what are particles typically made of, this is a picture taken from Chi-Sung's paper, compiling measurements with an aerosol mass spectrometer, mainly across the northern hemisphere. And what sticks out here is that regardless if you measure in inner city areas or remote areas, you always find quite some green in your pie. And the green in your pie here is the organic fraction of the particles with diameters up to 1 micrometer. There's also ammonium, sulfate, and nitrate always present in different amounts. Obviously, for sulfate, ammonium nitrate, well, that really already tells you what the composition is. But for organics, whatever that means, I mean, any organic molecule can be meant with that. And that's really pointing to a huge challenge and also partly why we have such huge uncertainties with aerosols and their direct and indirect effects, because the organics are made up of thousands and hundreds of thousands of individual molecules. So understanding this green part of the pie is really a huge challenge if you want to do it on a molecular level. So where does the organic fraction come from? So on the one hand, you have anthropogenic and biogenic activity emitting primary organic aerosols. So that is particles that are directly coming from the source and emitted into the atmosphere. On the other hand, both anthropogenic and biogenic emissions or processes emit huge amounts of volatile organic compounds. So that is gas phase molecules. And then in the atmosphere, they are oxidized. The VOCs are transformed into oxygenated VOCs, which can undergo gas-to-particle conversion, which then is forming so-called secondary organic aerosol, secondary because it has to go through the atmospheric chemistry pathway in order to form particles. Usually, the oxidation in the atmosphere is through ozone, the OH radical, and NO3. And I'm going to focus a lot on OH and NO3 oxidation in the following here. This slide here compiles what we know about both biogenic and anthropogenic sources of volatile organic compounds in the atmosphere. And what sticks out here is that on the order 90% of the VOCs globally come from biogenic sources. So there is an estimate that on the order 1,100 teragrams of carbon per year are emitted from the biosphere, where a huge fraction is really one molecule, it's isoprene. Then there is another fifth of this whole pie coming from the monoterpenes. There's other reactive VOCs and oxygenated VOCs, all of these coming from the biogenic emissions, and then only this small part of the pie coming from anthropogenic emissions globally. So that already indicates that you have quite some interest in biogenic emissions if you want to globally understand the sources of secondary organic aerosol. Also, what is known is that those biogenic emissions, at least when it comes to isoprene and monoterpenes, which are the two categories which are most well studied, they do depend on light and temperature. So what you see here is the normalized emission rate as function of light intensity for isoprene and monoterpenes, which are, in this case, emitted while they are produced. So that's the so-called de novo emission. So during the synthesis of those species in the plant, they are directly emitted, and you see there is a strong dependence on the light. So those are mainly emitted during the day. And then there is temperature dependence also present both for isoprene and monoterpenes emitted de novo. You see this goes through an optimum, a maximum temperature. And on the other hand, particularly monoterpenes can also be present in storage pools within the plant. So there you have an exponential increase of the emission with increasing temperature. So as those emissions do depend on light and temperature, that already tells you there is a climate dependence of those emissions, because certainly one of the things that we think of in terms of climate change is a temperature change. So Marco Kulmala in 2004 suggested that there could be a negative feedback involved in this formation of secondary organic aerosol from biogenic emissions. What we know is we have the biogenic emissions, we oxidize them in the atmosphere, we form secondary organic aerosol. With water vapor, they form clouds. So if you have an increase in carbon dioxide as a proxy for changes in greenhouse gases, you increase your temperature, you increase your biogenic VOC emissions, as you have seen from the previous slide. So that would mean you increase this whole sequence here. You have more biogenic VOCs, you form more secondary organic aerosols. There's some chance you would also form more clouds by that way. There is also an effect that carbon dioxide could really increase as a fertilizer, so to speak, your biosynthesis activity, which could also directly then increase your leaf area, for instance, or biomass, and by that increase this whole chain there. And as I detailed before, the clouds have a cooling effect. So if you increase the temperature, you would have a negative feedback loop involved here, where you have some counteraction by the secondary organic aerosol through cloud formation on an increase in temperature. And so the question is, does that really happen? I mean, that's a nice chain of thoughts. There's lots of rationale behind it, and it's easy to follow that, but the question really is it that way or not? So for a full evaluation of this, one really wants to know a lot of aspects, and this is just listing some of them which we can access experimentally quite easily and which we pay attention to. So you want to really know the BVOC, biogenic VOC source rate as function of climate factors. You want to know the global secondary organic aerosol source and the impact of secondary organic aerosol on the cloud properties. And so in terms of global secondary organic aerosol source, I mean, you've seen the chart where there's green everywhere. So organic aerosol is present globally. But how much globally is quite unclear. So this is compiling different kinds of approaches, bottom-up and top-down approaches of global secondary organic aerosol sources in teragrams per year. And what you see is that different authors come to very different numbers. So it could be anywhere between 12 teragrams of secondary organic aerosol per year to 1,800 teragrams of secondary organic aerosol per year, where the most recent publications indicate the most likely numbers are probably on the order a couple hundred teragrams of secondary organic aerosols per year. So there's huge uncertainties there. And then if we compare what is currently known in terms of modeling with our observations, this plot shows primary organic aerosol and secondary organic aerosol, and you always see the modeled concentration in micrograms per meter cube over the observations. These are log scales. So what you see for the primary within a factor of 2, which are these lines here, there's a number of data points, and within a factor of 10, we seem to understand the primary organic. But then when it comes to the secondary organic aerosol, there's a huge bulk of data down here, which is indicating we have much higher concentrations in our observations than we can reproduce based on our model understanding. And so this indicates for the secondary organic aerosol, there's huge gaps still open, and our knowledge is far from complete there. So what's known about secondary organic aerosol is that organics are everywhere in the atmosphere. The secondary organic aerosol dominates over the primary in most places. The biogenic VOCs globally dominate the sources of secondary organic aerosols, and the uncertainties remain on the total source of SOA. The models underpredict SOA. It is the yield of SOA from oxidation of given VOC mass is not well parameterized in models. And the biogenic VOC emissions parameterizations do only hold for isoprene and monoterpenes. So kind of almost half of the pie that I showed you, the oxygenated and the other reactive ones, are not included in the models. So the models really just pick up the isoprene and monoterpenes. So what we do in the Research Center Jülich to evaluate this loop, secondary organic aerosols with atmospheric oxidation and the coupling to climate, we perform kind of standard physical and chemical characterization measurements of aerosols in a number of environments. We do development of mainly mass spectrometric instrumentation and technique to either apply them for isotopic analysis or compound-specific measurements that are otherwise not possible. We deploy our simulation chambers widely. So in the upper part here, you see our atmospheric simulation chamber Saphir, which has a 250 cubic meters of volume. We can use very pure air in here and have solar light for OH production, and have done simulations at ambient concentrations. And down here you see a picture of a plant chamber where we directly use the emissions from plants to investigate SOA formation, which then really takes the simulation experiments for a detailed process understanding, where particularly the measurements with the real plants will be the focus here now. And then in the field, we perform measurements, for instance, on board the Zeppelin or at measurement sites. So for the measurements in simulation chambers, the aim here, and what I'm going to show you here, is that we want to study formation of SOA from biogenic precursors, where we really take the emissions from the plant directly and investigate which climate parameters could enhance SOA formation and evaluate which uncertainties are related to that, and in how far we can provide a robust parameterization or at least the basis for that for models. So the setup for the plant chamber is the following. What you see here is you have one chamber housing the plant. So in that chamber, you treat the plant as nicely as you can. So it is emitting the VOCs it would emit under, say, normal ambient conditions. You flush purified air through that chamber, taking up the VOCs and transferring them to a second chamber. And in that chamber, we do the atmospheric chemistry reaction part, where the relative humidity is typically on the order 60% and ozone concentrations on the order 80 ppb. We then use temperature to vary the BVOC emission rate for the plant, and then study how much oxygenated VOCs do we form, how many particles, we count the particles, we measure size distributions, and we measure composition of the particles. So this slide here summarizes some of the findings from those experiments. So you see the aerosol mass that is formed as a function of terpene concentration. So this is aerosol mass in micrograms per meter cube, terpene concentration for boreal tree species. So what you see is nicely linear dependencies. The more VOC you oxidize and consume, the more particle mass you form. We have very similar slopes of these dependencies for pine and spruce trees. So there the aerosol yield that we form is on the order 5%. And then for a birch tree, we had a yield of on the order 11%. Also what you see here is a line which was found by having a look into ambient data. So there, Peter Tunved and colleagues had a look into observed aerosol mass, organic aerosol mass in the boreal forest in Hyttala when they correlated their observed aerosol mass with the time that the air mass had spent over forested regions before arriving at the measurement site. So it was correlating with the pickup of monoterpenes along the trajectory. And what you can see is that that slope also quite nicely agrees with the yields that we derive for the main boreal tree species. And it's also in rough agreement with other people's work mentioned down here. Also, if we have a look into Mediterranean tree species, again, if we have trees which mainly emit monoterpenes, you see this nice linear dependence with a 5 to 6% mass yield. In this case, as I mentioned, we use the temperature to increase the BVOC emissions. Because we have a very strong dependence of those emissions on temperatures, already a 2 degrees increase in temperature would result in a 50% increase in SOA mass because of the strong temperature dependence of these emissions. You have seen before that the birch tree had much higher aerosol yields than the other trees. The reason for that was that in the case of the birch tree, we had much higher sesquiterpene emissions than for pine and spruce trees. So what you see here is for a spruce infested with aphids, the maximum SOA mass that we observe as function of BVOC consumption. And then these data points here are all data points where we have a relatively low contribution of the monoterpenes to the total emissions. So only 30% of the emissions are from monoterpenes, and the rest is sesquiterpenes. And there we have a high yield of on the order 17%, whereas here in this data point, when the monoterpene relative concentration was much higher, the yield was much lower, even though the total concentration was higher. So that's indicating that different classes of VOCs can have different aerosol yields, and it's indicating that sesquiterpenes are more efficient in producing aerosols than the monoterpenes are. So far what you have heard is that BVOC emissions are, as long as they are dominated by monoterpenes, efficient in SOA formation with a yield of roughly 6%. You have a linear increase in SOA mass formed with the increase of BVOC consumed, and sesquiterpenes have a higher yield than the monoterpenes. So because I mentioned that we want to have a look into how climate would affect this whole thing, is what happens to the SOA formation if BVOC emission patterns change when you change the temperature. So far, most of the temperature increases did not result, from the data I showed you, result in any of the BVOC emission patterns change. It was just increasing the concentration strength, but it did not change the pattern. And certainly one of the questions to understand why we underpredict SOA in models is there any BVOC or BVOC class which has an extremely high SOA yield and which we do usually not account for? You have not heard about isoprene so far, so obviously we should think of isoprene because it's a huge part of the biogenic emissions. So if we have a look into isoprene and monoterpene emissions, well, for the boreal tree species, monoterpenes are emitted from the pools, so they only depend on temperature, whereas the isoprene depends on temperature and the light conditions. So if we have a normalized emission rate over temperature, here black the isoprene and red the monoterpene, if you have at a certain temperature the same emission rates, increasing the temperature will increase the isoprene emission relative to the monoterpene emission, and vice versa when you decrease the temperature. So we had a look into, if we add isoprene to monoterpene emissions, what happens with our SOE yield? So what you see here is for a typical experiment, at time 0, we start the photochemistry, we start to produce particle number, and we start to produce particle volume. And this is data when we only have biogenic emissions of monoterpenes. If we add isoprene from a diffusion source to this mixture, this is what's happening. So not only do we not disturb the system by the isoprene being present, but we decrease actually the number and the volume of particles formed. Then after 3 hours, that doesn't come out too well here, we switched off the isoprene from the source, and you can see that the system kind of recovers, and we have an increase in particle number and volume after the isoprene is flushed out from the system. So the reason for this influence of the isoprene, which is not really what you would think what's going to happen, is the following. If you have a look into nucleation rate versus steady state OH concentration in those experiments, you see up here is the data pool where we have no isoprene added, so we have high nucleation rates, high OH concentrations. And at the point when we add isoprene, we decrease not only nucleation rate, but also OH concentrations. So it seems that in steady state, the isoprene grabs away the OH from reacting with the monoterpenes. The monoterpene oxidation products are the ones which do form new particles, whereas OH oxidation products of isoprene do not contribute to new particle formation. So we came up with a simple parameterization. When you look into the relative contribution of the isoprene to the total emissions, and have a look into the suppression of new particle formation from the addition of isoprene, you can see that with increasing contribution of isoprene, you increase or you decrease the number of new particles formed, where the exponent of this formula here is actually giving you the number of entities in the nucleus of new particle formation, and it's on the order 3 to 4 molecules or OH oxidation steps needed for new particle formation in these experiments. Also added here are lines for Finland in the 1990s. So this is the isoprene to total BVOC emissions in the 1990s in boreal forests in Finland. And this is projected isoprene concentrations or contributions to total biogenic emissions in 2100, where the major part of this change really comes from the northward moving of isoprene-emitting tree species. And even though the change here does not seem too dramatic, it would result in 20% less particles, and with that, a 12% less cooling effect just from the isoprene being added to the system. So changes in BVOC mixtures may not necessarily be additive. You could add a VOC, and that could decrease actually your SOA overall yield. And what I have not detailed a lot here, but what we found is that the OH chemistry is very essential in new particle formation, whereas it seems the ozonolysis products are the ones which are the massive part of mass formation. Other SOA precursors, oxygenated and other reactive VOCs are listed here, and most of those are emitted under certain stress conditions of the plants. And as you experience yourself, a tree is really going to be at the certain place where it's been planted for decades. So it's not going to move, the tree species are not going to move that fast as temperature change is going to occur, which leads to the assumption that more often trees are going to experience stress conditions and are going to be outside of their ideal temperature environment, for instance. And that could increase the stress-induced emissions. So the question is, what happens with stress-induced emissions? How effective are they in terms of SOA formation? So in this case, again, we had aphids infesting a spruce. We had on the order of 40% of the emissions being from methyl salicylate, so aromatic BVOCs having a large contribution in this experiment. And then the SOA yield that we observe is 22% compared to the 5 to 6% with monoterpenes. Also, if we have for instance, C17 alkenes, which we also observed under certain aphid infestation. We observed that there, in that case, again, maximum SOA mass observed versus BVOC consumption, we can end up with SOA yields as high as on the order of 30 to 40%. In that case, actually, luckily, we forgot to, at the weekend, water the tree. Yeah, I have to admit that. It was, we call it drought stress then in the paper, but what the tree does then in response to us not giving it water is it emits a lot of green leaf volatiles. So that's small alcohols coming from the tree. And what happens is that very similar to what happens in the presence of the isoprene, our SOE mass decreases dramatically, even though we have used a lot of carbon to oxidize and form SOA. So in a very schematic summary, what that means is as long as we are having monoterpenes and sesquiterpenes, our understanding at this point, and those are the emissions which are like constitutive emissions, so a tree under normal conditions is going to emit those species. You will move on a certain linear relationship where the more carbon you use, the more particle you form. But then under biotic stress, which is indicated here for the louse attack, but most biotic stresses seem to result in the emission of larger molecules which have higher SOA yields, so you get away from this linear dependence, whereas drought stress, for instance, will emit smaller molecules, mainly it's really the carbon backbone size, decreasing the SOA yield. And so what we had to look into in terms of the feedback is if you have a boreal situation, you have high monoterpene emissions from pools, there is hardly any de novo emission of monoterpenes and very low isoprene emissions. Heat and drought stress will, so for instance, increasing temperature will increase pool emissions. You have only minor effects of biosynthesis on the de novo emissions. So you increase your emissions, that will insert a cooling effect. So the blue stands for an overall cooling effect in the feedback loop. If we have biotic stress, we increase monoterpenes or sesquiterpenes, we increase alkenes, for instance, we have minor effects on green leaf volatiles. Again, that will increase our SOA mass formed and have a negative forcing overall effect. For temperate forests, the tree species there do not have that many monoterpene pool emissions, but they rather emit the monoterpenes de novo, and they also have rather low isoprene emissions. There, the heat and drought stress will rather reduce biosynthesis of the de novo emissions. So when the tree is under stress, it closes its stomata, and it's not going to produce so many VOCs. So that will have an overall warming effect because you will have less SOA formed. On the other hand, for biotic stress, similarly to the boreal forest, you will have increased emissions and thereby increased SOA. So to summarize this part here, the chemistry-climate interactions that were proposed, they do exist. The increase in VOC emissions usually changes SOA yields depending on the composition. So you really want to know which VOCs are emitted in order to answer the question, do we have a positive or negative feedback? And also the stress type and extent, heat, drought, or biotic stress, needs to be known and quantified in order to provide SOA yield parameterizations, which is still quite some challenge at this point. So we are not there yet to provide the modelers with simple numbers. So that's not yet happening. So for the last part of this lecture, I want to take a chance and tell you something about how to combine our simulation chamber measurements with ambient observations. So what you see here is from a recent paper from Dom Spracklen, where he tried to reconcile ambient observations of aerosol mass spectrometry with his model forecasts and say, how well do we understand the distribution of sources of both primary organic aerosol and secondary organic aerosol? And he says, in principle, we do well, as long as we think that we have biogenic SOA, which is formed through an anthropogenic enhancement factor, whatever that anthropogenically controlled mechanism is. So in order to reconcile observations with models, he has to plug in this anthropogenically controlled biogenic SOA. And that's really a huge source. If you have a look here, latitudinal dependence source rate, it's the vast majority of the SOA, which would come from that anthropogenically controlled process, whatever that is. So models have come up with suggestions what that anthropogenically controlled process could be. So there's currently actually two suggestions. One would be the nitride radical, so NO3 oxidation of PVOCs, because NO3 really has anthropogenic sources. And if the reaction of PVOCs with NO3 forms SOA, then that could be a large source of an anthropogenically controlled but biogenic SOA. And Habil in her papers suggests that if you include this process, 15% of the biogenic SOA production is expected to come from the nitrate oxidation on the global scale. Note that she really was referring to essentially one paper from the 90s where SOA yields from NO3 oxidation have been available. And everybody else in the community used to use ozone or OH in order to do lab work or chamber experiments for SOA formation from biogenic VOCs. And the other option would be oxidation of semi-volatiles from biofuel combustion. So because we have this nice simulation chamber and because we have instrumentation to measure NO3, and probably a number of other reasons, we decided to do experiments of SOA formation of biogenic VOCs with NO3 oxidation. So we did the measurements in the Safia chamber, obviously working with NO3 oxidation. You do not want to use the ambient light for reasons that that would photolyze NO3. So you would close this, shutter system. We use ultra-clean air supply from liquid nitrogen and liquid oxygen tanks to have pure air there. We add NOx and ozone for the NO3. Beta-pinene or limonene or isoprene were added for SOA formation. And then we use our whole equipment of field deployable, highly sensitive instrumentation for gas and particle phase measurements. And because we have such a large volume and relatively low surface, we can do that for a couple days. In this case, the longest experiment was 2 days. So our findings for the individual VOCs that we studied are different on the number levels. For the beta-pinene, we find an SOA yield from the oxidation of with NO3 of 50%, where the molar weight of the organic nitrate that we form is roughly 230 grams per mole. For limonene, the SOA yield is 25 to 40%, and we had some indication that also heterogeneous uptake of NO3 on the unreacted aerosol could happen because you have 2 double bonds there. And for the isoprene, we actually find that you have really 2 nitrate groups adding to the molecule, where the overall SOA yield is really pretty small. It's only 2%, whereas for the second generation oxidation products, it's 14%. All of these experiments were conducted performing aerosol mass spectrometry measurements on the aerosol. And what we find is that the organic nitrate in all of these studies has a very distinct mass spectral pattern. So the question there was to what extent can we take that pattern out for field measurements or apply to field observations and identify organic nitrate in ambient aerosols. Also what we found for the beta-pinene that from that 50% 50% mass yield, roughly 30 to 40% of the SOA mass was really organic nitrates. So there you really form a lot of organic nitrates. And if one applies this experiment with its yields to California, then SOA from beta-pinene and nitrate could explain on the order of 4% of the inventoried total California PM1. So that's really a large fraction. And a global estimate based on those measurements would indicate that you could have on the order 1 teragram per year SOA formed from just the beta-pinene plus NO3 reaction. So it could indeed be a large source of SOA and could probably really explain this anthropogenically controlled biogenic SOA. So for the field measurements, what we did is we took our aerosol mass spectrometer from our side, which is roughly here, Jülich is roughly here, to Cabau in the Netherlands. So what you see here is that depending on the wind direction, you would get clean air from the ocean or some inflow from the UK, France, or Germany, which has very highly densely populated areas to the east of this measurement site. Then here is the picture of the tower where we performed our measurements at the 60-meter platform. So we had a tube, a line, a sampling line going up to 60 meters. And this is the Zeppelin flying around the measurement site at the same time. So for the measurement intensive observation period of May 2008, this is a summary of our observations. So green is the organics, blue nitrate, red sulfate, orange ammonium, and pink the chloride. And what you see is that, well, first of all, we have relatively high aerosol concentrations with the axis here extending to more than 30 micrograms per meter cube. This is a remote or semi-remote area, so you would not expect many local sources there. The organics are dominant for most of the parts of the measurement period. And also nitrate is quite high in lots of the May observation part. So that nitrate really refers to inorganic nitrate. So the question was, if you see so much nitrate, what about organic nitrates? If we have high organics, high nitrate, there's probably a good chance to have organic nitrates present. So in order to evaluate that, what we did is we performed a positive matrix factorization of our observed organics. Here is the result of that. What is important to note here is that we have 4 individual components of the organics with different temporal trends and concentrations. And particularly this second organic factor here has a very strong diurnal pattern. So it's a semi-volatile thing, which is highly correlated with nitrate, and it's also highly correlated with the organic nitrate that we calculated from the observations here. So if we then take this information that we think we have a couple micrograms of organic nitrates present in this aerosol and plug in this VOC plus NO3 as an SOA source in a regional model. In this case, this is the URAT model. We do significantly improve the base case SOA forecast. So the red line here is what the standard model would have said should be there in terms of secondary organic aerosol. Black is the AMS observation of secondary organic aerosol. And then the pink line includes improvements in terms of temperature dependencies and so on. And mainly the improvement really comes from plugging in the nitrate plus VOC source into the model. In that intensive observation period that I'm referring to, we had AMSs deployed all over Europe. That's indicated here, and that was actually deployed over 3 intensive measurement periods. And what you see here is my split down of here in light blue the organic nitrate and dark blue the inorganic nitrate. So you can see that throughout the continental Europe and UK, whenever you have high nitrate, inorganic nitrate there, you can also expect to have quite high organic nitrates there, which back on the envelope would give a global organic nitrate source in the range of 2.5 to 10 teragrams per year. So the organic nitrate was representing, in those measurement cases, 30 to 40% of the total measured nitrate, and are found in all of the urban and rural sites. The estimated global annual organic nitrate source, as I mentioned, is on the order 2.5 to 10 teragrams per year, just from those European measurements, I have to state, which would be a substantial fraction of this so-called anthropogenically controlled biogenic SOA, which could be on the order 100 to 150 teragrams per year. And the findings indicate that there is a substantial potential for aerosol reduction through the control of anthropogenic NOx, obviously, because that would decrease your NO3 concentrations significantly. As an outlook, what we are currently trying is, and this is quite developed now, to have a plant chamber that can be directly coupled to our atmospheric simulation chamber, so we could do the chemistry under more realistic conditions there, and also have a look into more long-term aging of aerosol effects. So finally, just to summarize the 2 parts once more, we have chemistry-climate interactions through the formation of SOA from biogenic VOCs, and the anthropogenic enhancement of the SOA from biogenic VOCs is an interesting thing in terms of abatement strategies. And likely the NO3 oxidation of VOCs is much more important in SOA formation than previously thought. With that, I would like to acknowledge all co-workers and funding agencies, and thank you for your attention.
I'm sure we have time for a few questions.
I have 2 questions. One of them most people would expect not entirely serious, but with some scientific. One is a very simple question. Is there any identification? As a chemist, I would like to know what these organic nitrates might be, so that there's actually a chance to go and do some measurements or have an idea what to look for.
So
apart from a general molecular mass and the NO3 group attached somewhere to something.
For the experiments that we performed in the Sapphire chamber, all we had in terms of measuring the organic nitrates was a LIF approach, where you would thermally transfer your organic nitrate into NO2 and then measure NO2. And on the other hand, the aerosol mass spectrometer, which also really smashes down everything and then looks into the pieces, and from that tells you what it was. So we have, particularly for the beta-pinene NO3, we spent quite some time in doing some MCM modeling and improving the MCM model. So there are some suggestions what the molecular identity of those organic nitrates could be, but we have no proof of that. And anybody who can really well measure highly sensitive organic nitrates, let me know. I'd be happy to hear about it.
Okay, so there are some probably jobs for ambitious analytical chemists. But the second question is a little bit, I mean, you're talking about infestation with aphids or other pests, bugs, drought, stress, and so on. Most of the studies I know of are kind of short-term, because One thing I know not so much from basic scientific studies, but from owning a garden in Germany, that if you have those you all know what's going to happen in your garden if you have serious pest infestations after a year or two. I mean, you more or less, your plants start to wither and die and not going to be particularly healthy. So is there some study how that actually would affect? I mean, it's a little bit, if you look at forests that have seriously been infested by pests, they don't usually look very healthy, and I'm not quite sure how much they will emit. So the question is, have there been any study? I mean, surely you don't want to do this on an experimental global scale, and I'm not suggesting that this would be the solution to global warming or not having our forests die from pest infestations also. But have there been any impacts on how that would actually work on long term if the vegetation is no longer particularly healthy, if the whole metabolism kind of drastically changes, not just a first response to the immediate stress, which is different. That's certainly,
and that's why I mentioned be careful to know your extent of stress level also. So there's, as far as I'm aware, only one modeling study taking into account if you have bark beetle attacks on North American forests, what that would do in terms of monoterpene emissions and subsequent SOA formation. There, the authors assumed that every tree infected would ultimately die, and at that point, emissions are done. Actually, that's not really quite true. I mean, even a dead tree still emits monoterpenes, so for quite a long time. Actually, there's been this major storm in Germany 12 years ago, and they now have test sites there where they measure the monoterpene emissions from those trees which fell down in the storm, and there's still quite some monoterpene emissions there. So
for pine trees, even after logging, emissions continue.
So obviously, really to parameterize such events, it's really difficult because it's an extreme event. You don't exactly know when it's going to happen. And it's randomly occurring. So one thing, these aphids, which have the C17 alkenes, those are actually known by forestry people because in those aphids you have mildew formed, so the bees would come and feed on that. So they have some statistical knowledge about how often those aphids would be there, because in that year you have particularly much honey to get, and those are usually years when the fall before that has been particularly dry. So plugging such a thing into a global model that with kind of a half-year delay, you have a 60% chance of having such an aphid infestation is certainly something which is extremely difficult to do. So that's part of where the struggle really begins with all these stress-induced emissions, because those are not just continuously happening. They're locally, they are randomly, timely distributed, so, or not so randomly, but
I get to ask a question. So your work on the effect of isoprene on the monoterpene formation of secondary organic aerosols from monoterpenes. The parameterizations that you came up with, the question is kind of a multiple part question. Are these short-term parameterizations? And what I mean by that is, my simple thinking is that the effect of isoprene is to reduce the OH radical concentration, which is going to extend the lifetime of the monoterpene. So if you measure the amount of SOA at a certain time, you've formed less. But the monoterpene has to do something in the atmosphere. So in a real atmosphere, if it doesn't have other significant losses, well, you could transfer the loss from the day to night. Or if it doesn't dry deposit, it'll simply react the next day somewhere else with hydroxyl radical. So have you looked at that, or am I interpreting this wrong?
This is true. The one thing we are really referring to is particle number, not particle mass in this study. And nucleation is a thing that really has to do with supersaturation of vapors. So as long as you are close to the source, you're going to have a much higher chance of nucleating new particles than kind of when you are in a diluted environment.
That's true.
So our interpretation is that if you manage to take the nucleation out, it's still going to be fewer particles which are going to grow to cloud condensation nuclear sizes. Because the kind of downwind of the source, the oxidized monoterpene products are going to condense on pre-existing particles rather than form new particles. So there, the chances of forming new particles, which could then act as new cloud condensation nuclei, are smaller than kind of directly upon emission. So that's our interpretation, why that would really also in true world where you have all kinds of counter effects and can oxidize your monoterpenes later on, would still lead to less particle number.
Right. Okay, the second part of the question, yesterday during the defense, Marina's defense, we were talking about extending yields from chamber studies to the real atmosphere and the dangers of doing that. And the one thing that I noticed is that the OH levels were quite high in the chamber, 10 to the 8th, 10 to the 9, and we don't get beyond 2 times 10 to the 7, maybe 3 times 10 to the 7, which would be pretty high. Maybe the effect is linear. Maybe you get the same answer if the OH radical were the levels in the real atmosphere, but I'm not sure.
So,
have you thought about that?
Yeah, obviously. With a group focusing and specializing on OH radical concentrations, that was sticking out to us. So what's really very likely going to happen is that with these high OH concentrations, we are pushing the system into more peroxy-peroxy reactions than would happen in the ambient. It seems, though, that those peroxy-peroxy reactions could very likely be the heart of denucleation itself. So we are probably pushing towards nucleation with the high OH concentrations, and that could be that taking out the peroxy-peroxy intercounters then decreases your nucleation rates, and the peroxies from isoprene just being different in terms of their formation potential for new particles than the ones from the monoterpenes.
Okay. Further questions? You know what? I can do this.
Yeah, first of all, excellent presentation. Really enjoyed it.
Thank you.
My question is pertaining to the contribution of biomass burning to SOA. First of all, what proportion are biomass burning contributing to global SOA? And do you see any significance of that when you are modeling your results?
So I have to say that for May in Cabau, in the Netherlands, I mean, it was a really hot May. There's, I mean, biomass burning in terms of like heating purposes, I don't really see why that would happen. There could be long-range transport of biomass burning plumes from Russian wildfires also. I think as far as we know, the fire counts were low in that period. Let me go to this slide here. So the red here is the model understanding of what the biomass burning secondary organic aerosol would be in terms of latitudinal distribution. So first of all, it would be much lower than any of the other contributions. And secondly, it would certainly be much more important towards the equator, where you have much more biomass burning and biomass for that matter. There has been quite some discussion recently that in Europe, with households really switching to heating with biomass and burning wood or wood pellets, there's more and more biomass burning tracers that you can identify in particular urban areas, which have not been there or supposedly not been there some decades ago. So those inventories might be wrong by not really accounting for that change in residential heating. But that's probably pretty much what is known on that level.
Right. Thank you. My second question is with respect to warming, there will be more and more fires. So in reality, these forests will disappear. So have you taken that into consideration when you're actually projecting the increase in emissions effect of terpenes, et cetera?
So there's tons of interactions and aspects which one would really have to take into account to make a global forecast of what the biogenic emissions would be in 50, 100 years from now. So that's why we stop at the point where we qualitatively say, if then. So we do not go beyond that, because for the global models, you really need to have specialists applying their global model approach to it and taking all these feedbacks into account.
Thank you.
I guess there's also the, after a fire, very often you spawn faster growth, so the biomass growth is much faster afterwards. Any further questions? Peter?
Yeah, at the beginning you showed us lots of information on VOCs from cities and countrysides. What's the role of the oceans in all of this?
I know there's some isoprene emitted from the oceans. Beyond that, I'm not sure there's a lot known about BVOC emissions. So the current understanding, as far as I'm aware, is that for biogenic VOCs, the oceans do not play a major role. That picture is totally different when it comes to primary aerosol emissions. I mean, sea salt obviously is a big issue there. You have all kinds of primary organics that can be emitted from the oceans. But biogenic VOCs themselves seem to be a very minor contribution compared to the whole area that they cover.
There are some sources of Glaxol and methylglaxol from the oceans, and I don't think they've resolved exactly where they're coming from as well. So there is some SOA that can form from the oceans from those emissions. But yeah, it could be small. I'm not sure what it is on a global scale. Any further questions? Okay, if not, then I would like to take this opportunity to thank our speaker again.
Thank you.
And I understand you're here for a little bit, so you do some sightseeing. I apologize for the weather. But enjoy your stay in Canada.
Can I order different weather with you?
Have a good trip back to Germany. Thank you very much.